Hi there, this is a short video about solving one of those annoying problems when you need a stable DC high voltage, in this case to compare multimeters. Not having a precision high voltage DC reference with a known value, the procedure is comparing an arbitrary chosen voltage on the yellow multimeter with what is shown on a reference instrument, in this case the blue meter. 12 volt AC from an isolation transformer are connected to the secondary of the transformer you see here. Its primary is therefore producing a doubly insulated high AC voltage shown by the red meter. This high AC voltage goes into a full bridge rectifier and a smoothing cap, all squeezed into the terminal block. The DC is then measured by both meters. You can see the problem. The voltage is continuously fluctuating because the AC, ultimately coming from the mains, is just not very stable. In this demo, the effect is relatively mild, but depending on the time of day, the fluctuations can be much more severe, such that it's hopeless to compare two instruments. While reading the voltage on one, the value is changing already, so the second meter reading can't be compared with the first one. Clearly, I would need a stabilized AC as input for this setup, but sufficiently stabilized AC power supplies are rare, and those that exist are big, bench or rack mounted monsters and prohibitively expensive. This module on eBay offers a different solution. It's a DC to DC step-up converter producing between 90 and 200 volts from 10 to 15 volts input. There are quite a number of these modules available because their main purpose is to produce the high voltage required to drive Nixie display tubes or valves, and Nixie-based clocks seem to be currently very popular. I looked at quite a number of high voltage DC to DC converters because for me the point is not to produce very high voltages or to drive lots of Nixies. My main criteria is that I want the output to be adjustable and as stable and ripple-free as possible. With 13 British pounds delivered, its price is already on the high side as DC to DC converters on eBay go, but I decided on this module from seller Benjamin1292 because mainly they actually spent the effort adding some real technical specs other than just the output voltage and module dimensions found on most of the other listings. As you can see, they claim to have improved the design and reduced the ripple from 105 mV down to 30 mV, and very commendably specified the test condition, 180 volts, 30 milliamp load to measure this. 30 milliamps may not seem much, but at 180 volts that's almost 5.5 watts. The load resistor of 6K needs to be able to handle this. It is certainly more than enough juice for my purposes. It took only 3 days for the board to land on my bench. It is very small and looks almost old-fashioned in the use of a single-layer PCB and only through-hole components. On the other hand, this makes it eminently repair and modification friendly. The switching regulator IC is even socketed. The additional ripple filtering is probably an LC filter on the output, judging by the second inductor next to the orange output connector. The underside reveals a very straightforward design that can be easily reverse engineered if needed. As promised in the eBay listing, the 8-pin switching regulator IC is the venerable 34063A, boosted for high voltage by a separate driver transistor and an N-channel power MOSFET IRF640 for doing the actual switching. It looks as if they have not skimmed on component quality either. Good sized resistors, the black caps are from Rubicon no less, and the brown ones from Nippon Chemicon. The 34063A chip itself goes back a long way, certainly more than 10 years. I don't mind it at all that this board is using a tried and trusted chip as a controller. It has an internal 1.25 volt reference with 2% precision, which is nice, but since I'm going to adjust the voltage manually, the absolute precision of the reference isn't as important to me as that it's very stable because it's internally temperature compensated. I want to be able to change the voltage easily, so the provided adjust once and never touch again trim pot won't be suitable for me. For one, it would be rather awkward to manipulate, and more importantly, mechanically trim pots wear out very fast if you use them often. So it has to go. Helpfully, the printout of the PCB states that it has a value of 5K. And the traces on the back show that we only need 2 connections. Because the unit is so hackable, it is very easy to desolder the trim pot, and I put a 2-pin connector in its place. It is actually a 3-pin connector for Dupont sockets with the middle pin removed to fit the existing holes in the PCB. I made a little cable and matching connector for a proper 5K potentiometer to plug right in. The red multimeter shows the input voltage and the blue the output. The unit is loaded with 2 rather big 3-watt resistors in series for a total for about 20 kilo ohms, which at the lowest setting of 85 volts means slightly above 4 milliamps or about 0.4 watts. Let's crank it up a bit. The maximum is 209 volts at 20K load with 10.5 milliamps current flowing or about 2.2 watts. The resistors are getting pretty hot already. Let's reduce it to a more moderate 150 volts or so. And watch the output voltage for a bit to see how much it fluctuates. As expected, the voltage is very stable. Turning the power off, with 20K load, the output discharges almost instantaneously. Given the high voltage, I decided to put this into a little box for safety. Here you see the front plate. I simply designed this front plate on the computer, printed it on normal paper, laminated it and then cut it out. As you can see, this box was used for other stuff before, and the new front printout neatly hides some of the now unused holes. The board will sit on these 4 spaces that are glued onto the front plate. This simplifies wiring and makes the unit very easy to maintain. The DC to DC converter contains some rather beefy output capacitors, and if no load or only high impedance devices like multimeters are connected, a dangerously high voltage will remain for many minutes after turning power off. For this reason, I had planned to put 2 1 megohm resistors in parallel across the output as a 500K load. The value is sort of a compromise. I want a relatively low resistance to discharge quickly, but low resistance means lots of heat in the resistors while the unit is powered on. If you remember, at 200 volts a big 20K 3-watt resistor combination got too hot to touch within seconds. Most of my high ohm resistors are 1/8 of a watt or 125 milliwatts, so the 80 milliwatts of a 500K resistor at 200 volts will get it quite warm already. 2 1 megohm in parallel means that each has only 40 milliwatts or 1/3 of its nominal rating to dissipate, which is just about acceptable. On the downside, the low current through a 500K resistor means the discharge to safe voltage levels at power off will take half a minute or so. So in the end I came up with a last minute design change, as frequently happens in my projects. Why not make use of the current flowing through the 500K resistor to drive a small red LED? The LED will clearly show that high voltage is present, and once the power is turned off, the discharge will keep the LED glowing until the voltage decays enough to safely touch the terminals. Wiring of this simple module takes no time at all. 2 input wires and 2 output wires are all there is. You can see the resistors and the last minute addition LED bodged in between the output terminals. It kind of looks neat below the high voltage sign, as if I had planned to put a light there. The front panel cover got a bit crumpled by the drilling of the hole for the unforeseen 3mm LED, but it's barely noticeable. Paper, even when laminated, doesn't drill well. It is far better to use a hole punch, but in this case that wasn't possible anymore. Putting the completed unit into the box and inserting the screws to secure the front plate are the finishing touches of the assembly. Time to test the unit. The LED is clearly visible already at 85 volts. The camera exaggerates the LED brightness somewhat, but it's certainly visible, and even with the naked eye it does get noticeably brighter when the voltage is raised to 209 volts. When turning the power off, the 500k resistor and to a tiny bit the 10 megohm impedance of the multimeter drain the output cap, and the LED gets dimmer until its glow under normal workbench lighting becomes just about invisible when 15 volts or so are left. As a reminder of the original problem I wanted to solve, here's a repeat of the scenario from the start, but all that AC transformer stuff being replaced by the neat DC to DC converter box. Let's test the cheap yellow meter at about 150 volts. It is actually not bad at all. And see how stable the voltage is, making these tests really easy to conduct. I'm quite happy with this result, and if you are in the market for a stable high voltage DC source for up to 30 milliamps current, this unit will do the job nicely, and in one of my next videos I'll show how to use this box to produce a stable high AC voltage as well. Thanks for watching.